Hello, welcome to Lady of Brussels. Today we are talking about the subject "The future is not fixed." It's the subject about climate change mainly, and today we have participants. This is Sophie Opfergelt, Aernoudt Jacobs, Sebastian Sterl, and our moderator today, this is Frank Thijs. Frank Thijs is a Belgian visual artist and filmmaker renowned for his video installation experimental documentaries. His work, mostly notable the trilogy Technocalypse, deeply explores philosophical intersection of technology, science, and society. Blending visual art with critical theory, he examines the future of human evolution and existence in the digital age. So I would like to give the floor to Frank, and so welcome to Lady Talk Brussels.
Hello, everyone. Thank you. We're gonna have the three speakers tonight, each like about 20 minutes. Then we have a little talk among each other, and then some questions, if they are from the audience. And then it will take like almost an hour and a half or something, I guess. So I think we start with Sophie. So she's a Professor Dr. Sophie Opfergelt. She's a senior researcher in geoscience at the Earth and Life Institute at the UCL Louvain in Belgium. And her work is mainly focused on the research of the permafrost, particularly how the permafrost is active in chemical, biological, also in the winter, because most of the time, or until now, it has always been considered that in the winters, when everything is frozen or so, there's hardly any activity, so it's never been used in the calculations of climate change. And so I guess she's going to say now something else about it.
Good evening. Thanks for coming, and thanks for your interest in the topic. So indeed, the future is not fixed, and the permafrost is a perfect example of a system in transition that is definitely dynamic and changing. And I want to illustrate with a number of research activities that are ongoing at UC Louvain together with partners in different universities in collaborations. So I want to start with these pictures that is been taken in September in Abisko in northern Sweden. And I'm telling you that this is a ground on permafrost. So beneath your feet, you can see, maybe I wait a minute. Okay, so maybe this is not the typical Arctic landscape that you have in mind. Usually people imagine the Arctic always white and snowy and icy, but we have to bear in mind that there is a summertime in the Arctic as well, with no snow during the summer, but still beneath our feet, so we are sitting here in the field, and at 50 centimeters beneath our feet there is the frozen ground. This is a typical landscape of the northern Arctic. This is a peatland in Abisko, so there is permafrost in Europe, and more generally, everything that you see in purple here in the landscape is permafrost. When it's dark purple, it's continuous permafrost, so it means that above 90% of the ground is frozen beneath your feet, and when you go with lighter color, it's less and less percentage of the ground that is frozen, where in these very light areas, this is about only 10% of the ground that is frozen. On top of the permafrost, so the permafrost is defined as a layer that is below 0 degrees for more than 2 years consecutively. So it's called permanently frozen. On top of that, you have a layer that seasonally thaws and freezes again in the winter. So it thaws in the summer and freezes again in the winter. This is the active layer. This is normal in the system that a portion of the ground thaws when it's warmer in intense summer. What is not normal is that now this is getting warmer and warmer, so that active layer is deepening and it's getting more and more into the permafrost. And with the winter temperature, it's not cold enough for a super long period, not for a long time enough, to refreeze everything. So it means that a portion of the ground stays unfrozen during the winter. And this is called a tally. So here we are sitting inside a permafrost tunnel. So everything around us is frozen. This is a frozen ground. You can see massive ice here. This is a permafrost tunnel in Alaska. And this looks like very well structured. But when you thaw that amount of ground with so much ice, this is absolutely muddy. So it means that the frozen ground is structuring the system. If you lose the ice, you lose the structure. So if you imagine this is happening at the scale of the Arctic, we call this the active layer thickening. So what I call the active layer, that layer that thaws every summer, is deepening. And if you look at the evolution since here, this is over the last, so 2019 is the last one, and it starts from here, 2000. So you see the evolution, at least 50 centimeters deeper, the ground has been thawing over that amount of time. So that means that this amount of permafrost has been lost. And here there is an example of trees in Alaska. They are called drunken trees, because if the ground is thawing, the trees cannot sit anymore. So these are called the drunken trees. If you imagine at the scale of the Arctic, there are 5 million inhabitants living in the Arctic. So this means here you have the settlement closer to the coast and also the inland. Among these 5 million inhabitants, about 3 million of them are on a ground that is currently facing massive thawing problem, and that where the permafrost is actually at risk by the end of this century. So it means there is projection, depending on the different scenarios, that the permafrost is lost in some of these settlements. That poses large problems for the people living around the Arctic. I'm going to show you some examples. The first obvious example is the infrastructure, because you lose the ground, you lose the ice in the ground, so you lose the structure. These are examples of, this is a road in Alaska, where we go on the field in that area. 5 years before that photo, the road was perfectly flat. And then with the ice melting, the ground is progressively becoming wavy, as you can see here.
It's a drunken road.
Yeah, it's a drunken road. You cannot be drunk on that road because it's very, very bumpy and very dangerous. Another example here in Yukon in Canada, you can see those advertisements for permafrost affected area, very dangerous road to take. More importantly, what you need to put that in context is in the geological timescale, that permafrost is an heritage from the glacial period. So this is a picture of 21,000 years ago, where there was an ice sheet on top of Canada. And the roads that I have taken as a picture, they are circled here in red. And they are sitting in an area that were just on the side of the ice sheet 20,000 years ago. And beneath the ground, there was ice-rich permafrost. So now this ice is melting, and this is what is causing these roads to collapse. So we have to bear that in mind, this context of the glacial period. More importantly, local effects are not only affecting infrastructure, but also the biogeochemical constituents that are included in the ground. So we have pollutants, we have different chemicals that are the legacy from industrial sites that were built in the Arctic. And we have also some pathogens. These are frozen in the permafrost, and now because the permafrost is thawing, some of these components are being released in the environment. There is a very active research going on, and so far what I would like to explain is that there is no such thing of a zombie virus that is usually taken up in the media. That is not true. So there is no evidence for any direct infections of humans from any pathogens from the permafrost. Right now, this is very improbable because there is a need of a number of hosts to transmit anything to the humans. So we have to be careful with these announcement of zombie virus. One thing that is not local, but that is a more global effect is that the permafrost contains carbon, a stock of carbon that is twice as much the amount that is in the atmosphere. So in the permafrost, you see here you have 1,600 gigatons of carbon. That is twice what is it in the atmosphere. It is thought that about 5 to 15% of that amount will be released in the atmosphere by the end of this century. And this is what is currently not taken into account in the carbon budget, because this is considered as a natural emission, and it's getting increasingly higher with warming the permafrost, but it's not taken into account in the current carbon budget. What is the consequence of releasing that carbon from the permafrost is that it is releasing, so actually at the moment the carbon in the permafrost, this is leftover from roots, from branches, from leaves, that is as a solid carbon. But when it's thawing, it's exactly like if you unplug your freezer, it's decomposing and it's emitting greenhouse gases as CO2 and methane, and that is increasing and contributing to rising the air temperature, and then again warming the permafrost and thawing the permafrost. So this is what we call the permafrost carbon feedback. As part of the research that we carry at UC Louvain, there is this question that the carbon is not alone in the ground. The carbon is also in presence of minerals, other constituents from the soil, and they can bind together. So a portion of the minerals can actually maintain the carbon in the ground and prevent this carbon to be emitted as greenhouse gases. But there is a very big open question is how much the change that the permafrost system is undergoing is going to affect these bindings. So are we going to unlock these interactions between the carbon and the minerals, or are we going to provide more way of the carbon to be bound to these minerals? So we pay a very close attention to the change in the water, in the ground, and to these interactions. And one question that we look specifically with a tool that we have developed at UC Louvain is how much these interactions are stable. Do we consider that they are preserved over time? So that means there is no dissolution, they are very well preserved. Or do we consider that they can dissolve, then release the carbon, which then is vulnerable, and then reform? To look at that carefully, we use a tool, an isotope tool, that is looking at the association of this carbon and iron with an element that is the strontium, that has a different isotope ratio if you have no dissolution or if you do have this mechanism of breaking. So we can look at this change. To do that, we go on the field here in Alaska and we collect permafrost samples from along a tall gradient with different levels of water saturation, different levels of humidity. And we extract the carbon and mineral association to be able to extract the strontium that is bound. So from the field, we go to a clean lab. So it's a lab where you have to avoid contamination with your sample. You have to wear white cloths, and this is air filtered. You purify your sample, you pass it onto a column to purify the strontium, and then we go to a mass spectrometer that will collectively measure the different isotopes. So this is a lab that is based in Louvain-la-Neuve. And the most important finding is that the water is the key in this system, because the only location in the soil where we found that these associations were dissociated and then reformed is at the level of the water table. So above, when the soil is always dry, there is no change. And when the soil is always saturated, there is no change either. The problem is where there is a water fluctuation in the soil. This is exactly where everything gets destabilized. So water pathways are essential. And we have been looking more extensively to a number of other processes by paying attention to this, including nutrient sources for vegetation, and also the lateral transfer, the export of the carbon from the system. And to look at that, you realize now that it's not only a question of looking at the soil profile, but it's more a question of a landscape question. So that's why we have to tackle this question across the disciplines, and that's why we work together with different colleagues in different disciplines, including the geophysics, the remote sensing, the climate modeling, because we need an approach that is cross-discipline to understand what's happening in this system. And it's not only located in the ground. Now, to illustrate this approach, I want to bring you to again to Abisko, where I started the talk, in northern Sweden, at a site where we have degradation. At the site this is called the Palsa. The Palsa is the stable site. At this site, you have the permafrost that is at 50 centimeters beneath your feet, as I said earlier. But within meter scale, you have a collapse. And there, in the degraded area, you have no permafrost below 150 centimeters. So it's really degraded. And this is a degradation that is very meter scale, so very close. The work that we've done there is using a drone, high resolution, looking at the topography of the soil and the vegetation. We have quantified how fast this change is going between the year we've been, was 2021, and measurement that were done 2 years earlier, 2019. And the degradation, we actually quantified that annually it was getting 5 times faster now than another period in the past between 1970 and 2014. So there is an acceleration of the collapsing of the system because we lose the ground. The question is now, this is what we can see from the surface, but underneath, what's happening? Considering that this is something we cannot see from the surface, we have been sampling the soil pore water and looking at how the chemistry of that pore water was affected by these changes, especially the carbon and the binding with the mineral that I told you about. And we can see that, again, the water saturation is playing a major role, because when you collapse, you end up with a very wet area. And so you change the association that the carbon can make with the mineral in the soil, and only within meter scales. So this is a massive change for the system. But as it was said in the introduction, this is something happening in the end of the summer. But what's happening in the winter? We think that when it's snowing and it's freezing outside, nothing is happening. It's just dormant or quiet. But what's really happening in the winter is that you have a transitioning period between your summer and your winter. You have a long period that is called the shoulder season. You have a shoulder season between the autumn and the winter, and you have another one at the end of the winter before the spring. These transitions period, they are prolonged ways where the ground is not yet completely frozen. You have snow on top, but underneath you have a thawed layer, and it takes months before it's actually frozen again. So underneath, it's not boiling, but it's active, let's say. You have water, you have your ground, and you have biological activity, so it's still possible to have decomposition. And so with the team, we have been looking at that more carefully at this exact same location in Abisko in Sweden, and along that same transit from the Palsa to the degraded Palsa, we see that the snow is playing a very important role, because we are still early winter. There is snow, and then sometimes positive temperature, snow is melting, but the ground is not frozen. So you have water infiltration. That means you can have the water table to rise, And again, you change the water condition in the ground because of the snow melt. So it's clearly active in the winter. And what it does in addition to rising the water table, the snow is acting like a flush. Because we have a slope here. And so you imagine you bring a large amount of water from the snow melt, and this is acting as a flush and flushing out carbon and minerals out down to the river. So beneath this, our feet in the winter, there is clearly still a dynamic flow out of the system that is exporting carbon out of the permafrost. And with that, I hope that I've convinced you that this is not only the summer that is the most important period. This is definitely the shoulder seasons that are playing a big role. And now we are focusing our activities deep in the winter, where I told you about these layers that are called talics that stays unfrozen the entire winter. So this is hard to collect water from these talics because it's really freezing outside. But this is where we are currently focusing a lot of our activities. And if you compare a same situation, this is in Alaska, where during the autumn, you see these colors from the autumn. You have a water track that is bringing down water across the sites. And the same water track, a month later, in that transition period, covered in snow, you can see that in these water tracks, the snow is accumulating and is actually playing a role of like a duvet. You really insulate the system, and it's warming. So the ground is thawing much more deeper in these water tracks. It's very getting warmer and deeper in the permafrost. So this is an area where now we are focusing research, including geophysics, as I said, with colleagues coming up with radar to detect the depth of the permafrost, collecting the water. And also, I want to bring to your attention a work that I am currently doing also with an artist. She's a professional dancer and choreographer. And we are working on how to show with the movement the dynamic of the fact that this ground is really moving, is thawing, but this is creating movement and scars in the landscape. So we have participated together to this Living Art Festival in October. Her name is Louise Van Est, and we continue this collaboration to be able to actually look at this transitioning system. And with that, thank you for your attention, and I'm happy to answer your questions.
We're not going to ask questions now yet, so we continue with the next speaker. That's Aernoudt Jacobs. So Aernoudt is a sound artist, basically. He makes installations, but mostly focus on sound, create sounds in specific environments, and record also in specific environments. So he works in a quite conceptual way with sound, and he made one project that is called Permafrost.
I will talk about my practice in general first, having some installation examples that I will go through, and then afterwards I will talk about an installation called Permafrost. It was made in the year 2007, between 2007 and 2009, and so I will talk about this installation, how it was exhibited, but also the research behind it. So I'm mostly working with the medium of sound, like you said. My work is mostly phenomenological, and I'm working a lot in empirical ways. So my creations mostly originate from intuitive research in the field of acoustics, technologies, and also perception. So mostly I'm trying to explore how sounds can trigger sonic processes that affect the perceptual field of the observer. So my work is a study into everyday sounds. So I often start with field recordings and everyday sound recordings, and then I process these recordings after having a relationship with them, and then I reproduce sound compositions, but also in combination with objects and installations. So my work is mostly about the complexity, richness, and the layering of our daily environments and how you can experience this. And most of my work is developed together with scientists in labs and also universities. This work that you see, it's an installation that is called induction series, and I am suspending coils, magnets, and also cans into the air, and I use electromagnetic inductance to induce sounds into the cans. So by using electromagnetics, magnets, I can create some vibrations into these cans, and these vibrations, they are of course they are sounds. So I make recordings of sounds, and then they are induced into these cans. And you can also enter these installations at the other side. And then there's another installation around the photophone. This is an installation that I created some years ago also, and it's around the photoacoustic effect that was discovered by Graham Bell in the 1800s. And what you can do with the photoacoustic effect is that by applying a strong beam of light onto a material and you let it vibrate with this light, you can create a sonority. So you can hear the sonority of the material by inducing light into it. So for example, the photophone, here you see there's a laser beam that is activating a photoacoustic cell. That's the most light part in the installation. And then this is connected to a large cone. And this amplifies naturally the sound of copper. And then you can hear by the reflection of this part, you can hear the sound that is amplified. I use the same principle with the heliophone, and here I capture the light of the sun, and there's a wheel rotating and also activating a photoacoustic cell that amplifies the sound. So here I use the light of the sun and the ephemeral aspects of the light in the clouds, of course. They change the intensity of the sound, but also the nature of the sound. Here, can you hear the sound?
Because the sun is only see now and then that there is some fluctuation.
Yeah. So what happens here is that the light beam is being chopped by this wheel, and this creates a vibration. And this vibration is captured into the copper element that is inside this photoacoustic cell, and this has slight vibrations because of this. And then, of course, the horn is amplifying this sound. Another installation that is being developed now and already shown in Leuven last year. This is humming the Ubik. This installation is capturing electromagnetic waves that are around us everywhere. So I capture these waves with different antennas in different locations of Leuven in this case. And these electromagnetic waves are transformed into voices with an AI model, voice models. And so for this installation, you see these mosaic kind of tiles. These are in fact light-emitting panels that are amplifying also sounds. So you have a combination of sound and light happening, and this creates different sounds in each panel. And these are all voice sounds. I don't have a sound sample of this, but this gives an idea of how the sound and how the light is changing into the space. And then we have permafrost. This is an installation, like I said, I developed in 2007 and 2009. Between these periods, I showed it in different places in Belgium, but also abroad. It's a sculpture work that is amplifying constantly, freezing and melting at the same time. So you hear the crystallization process, you hear the expansion of the ice, the thawing, so the water, the ice becoming water. And for this, I had to develop several parts. And one of the first parts that were developed during residencies were how I wanted to present the work. But further down here, I had to create microphones, special microphones, to know how to amplify these sounds, because you have a material that is first water and then it changes into ice and then it goes back. So it's a very tough environment. So we needed to find different types of microphones to amplify this. We also built some acoustic enhancers. So these are plates that are inside the installation, and these plates, they capture, of course, the movement of the ice, and naturally they vibrate and you hear the sound also. So this combination of acoustic sounds that are not amplified, but also amplified sounds. I'll give you a sound sample. This is the melting process of this object.
What were the ticks? The ticks are the track, yes, and it's a big track.
So what you hear is also a buzz, constant buzz. Of course, by building this thing, it becomes a very big microphone, because it's sometimes it's very liquid, and then the sound is different. But when it's very thawed, then it becomes very conductive. So every movement in the room also is also amplified. So it became the combination of environmental sound of the space, but also the active parts that you hear with the microphones.
And when it's not melting but freezing,
so this is like, sometimes you hear more a liquid type of sound here, For me, it's very clear the difference. And then when it becomes thought, then it's much harder. It can be also much louder also, because of course the expansion of the eyes is very strong, and it reacts on these small microphones that are very sensitive, and then it becomes very much harder and much faster also the sound, because also this aspect of sound into eyes is much faster because it's a hard material. So the speed of sound is like 3,300 meters per second. In air, it's like 340 meters per second. So that's much slower. So the nature of the sound is much more direct. It's looping, I think.
Every digestion.
Have you managed to generate a musicality out of it? With all the sounds that you have recorded, from all of that?
I never made a composition of it,
yeah,
because I really see it as an installation. But at one point, for example, we did a presentation in Ghent, and there was also a drummer playing with the sounds.
Okay.
Yeah, so he was like interacting with it. Yeah, so that was the most direct musical aspect of it. Yeah.
We can come back on, so you can ask
Sorry,
questions when.
sorry,
I'm trying sometimes just but a small question. But,
So here, that's the frost machine. So this machine is making the eyes. So it's a quite big machine. And we work together with the University of Hasselt to create a machine that is as ecological as possible. Because we needed to make an installation that is not only freezing, but it's also melting. So we had to find ways to use the heat of the system, because it generates a lot of heat to make ice. So we use that heat to melt the other part of the installation. And so other parts, for example, the coolants, the liquids that are inside the tubes, they are derived from betaine, which is a beetroot, a beet sap, juice that can be very cold. Yeah. So this is like the installation, how it looks like. So on the left you have the melted state, and on the right you have the frozen state. The cycle is around 2 hours, and you could see it as a synthesis, I think, where you have on the one side you have a liquid phase, and then on the other side you have the frozen phase, and then it's kind of a constant double state that you see, in fact. And then there's also the aspect of the presentation. So mostly the installation is presented where you have the sculpture, the ice sculpture on one side, and on the other side, what is not shown is the frost machine. It makes a lot of noise, and so what we try to do is to isolate as much as possible the machine, but sometimes it was visible in some spaces, or it depended on the presentation context also. And then around the installation you have the loudspeakers. These are these sheets, special sheets that are called piezo foils. They use piezoelectricity to amplify, so you can create with Piedofol you can create speakers. And so this is the only thing that you see. You see the installation and then these sheets, and everything is amplified through the sheets. And then I have a stop motion movie about the installation. It's showing the melting stage of the installation.
Is the sound also now faster or no?
No, it's only part, slow part.
Is it the sound from the freezing?
From the
Melting.
melting.
Oh, it's not.
Melting, yeah. And then later you will hear the freezing parts. This is the freezing part. Okay, that was it.
Okay, thank you. So then, as our third speaker, we have Professor Dr. Sebastian Hendrik Sterl. He's a researcher, a professor at the VUB, at the Department of Water and Climate, and is also an advisor for the European Commission on climate. One of his main research interests lies in the investigation of the vulnerability and the resilience of the future renewable-based electricity systems, especially in the global south. He will talk now about, so he has done a lot of research in Africa, but currently he has been done, his last research was in Ecuador.
Bonsoir, goedenavond. I'm not going to talk about permafrost, also almost not about climate change, but a little bit about water. Yeah, so this presentation has the maybe somewhat cryptic title, Fortifying Ecuador's Power System Against Drought-Driven Energy Crisis, but I will explain what all of those words mean. Let's see, voila. So where does Ecuador get its electricity from? Most of it, as you can see in this graph, is hydropower. So about 3/4 of the installed capacity in megawatts of Ecuador's power system is from hydropower plants. The rest is a lot of thermal power plants, so diesel or gas, and a bit of wind power. But hydropower is the backbone. And this is logical when you look at the topography of Ecuador. On the western side of the South American continent. It's a relatively small country here, bordered by Colombia in the north, Peru in the south and the east. On the west, there's the Pacific Ocean, and Ecuador is bisected from north to south by the Andes mountain range, yeah, with peaks of up to more than 4 kilometers high. So that divides the country into a Pacific side and an Amazonian side. All the water on this side here eventually ends up in the Amazon River. And so you have very steep drops of water, both westward and eastward. So the geography allows for the opportunity to exploit hydropower potential, right? Because you have rivers and they drop over steep inclines, so you have what you need to generate power from hydro turbines. And so Ecuador has a good amount of them. The 10 biggest ones are listed here, but in reality there's several dozens of them on both sides of this divide, which is interesting because the rainfall regimes and the river flow regimes on both sides are somewhat different. Even though the climate is connected, they're not independent of each other, but usually the flood peak in the rivers arrives a few months later on the Amazonian side as compared to the Pacific side. So you have some complementarity, that some of the plants are dominant in one season and others in another season. That's the basic idea. So historically, there's been an interesting development. This graph shows, this is from a reproduction of what actually happened according to our models, but it's more or less corresponds to reality. Power generation, gigawatt hours per year, starting in 2011 up to 2024 in Ecuador. So the blue colors are basically hydropower, different forms of generating hydropower. The dark gray here is what is added by the thermal plants, diesel and gas-fired power plants. And the black line here is the total electricity demand. So, like in many developing countries, electricity demand is rising as economies are growing. So the country needs to add more power plants to respond to that demand. And Ecuador decided in the last decade to invest mostly in new hydropower plants. So you can see that starting at the beginning of last decade, there was strong investment in expansion of hydropower capacity, building more hydropower plants on both sides of the mountain range. And this worked. So the hydropower generation increased from year to year. At some point, 2018, 2019, almost 100% of the power generation was coming from hydropower. And some quantities of the hydropower could even be exported to neighboring countries. But then something else happened because demand kept growing. But the climate started getting somewhat drier in successive years. So hydropower started decreasing again until an El Nino event in 2023, 2024, which really led to a very sharp drop, especially in 2024, of the hydropower generation. And that in the end led to an electricity crisis, where you see some part of the electricity demand in the end could not be satisfied. There was not enough generation capacity in Ecuador anymore, based on the water that was available in the reservoirs. And this was disastrous for Ecuador. So various newspaper articles across the world reported on this. Some people were saying it's like the government basically had to implement blackouts of up to 12 hours a day, or more people were saying it's like going back to the 18th century. Hospitals that were without power for prolonged periods of time. The New York Times wrote that Ecuador put its money on hydroelectric power, but then the rivers stopped carrying water. Yeah. So let's say both the social implications for people well-being, but also the economic implications for businesses and industry in Ecuador were actually very disastrous. So in my team, we were interested in looking at potential strategies for how this could potentially be mitigated in the future. It might happen again. We don't know if climate change might make it worse. It could happen that in the future even worse events happen. So we need to come up with strategies that somehow help to make these situations better. Of course, a simple solution could be to say we will just build more thermal power plants, and then you cover the shortage with gas or diesel. But this actually didn't work too well during the crisis in 2024, because it isn't. You can have the thermal plants. That doesn't mean that you magically have gas and diesel to burn in the moment when the crisis happens. And Ecuador tried this, but actually couldn't procure enough gas and oil to run the thermal power plants at full capacity, which contributed further to the blackouts. So can we think of a situation where we don't have that limitation, where we don't have to rely on emergency import of these fuels? Now, of course, I've already mentioned this complementarity between the Pacific and Amazonian side, which have different profiles. This is an interesting idea, but it didn't work at all in 2024 because the shortfall, this graph shows the shortfall in river discharge in 2024 compared to the average of the most important rivers with hydropower plants in Ecuador. And this shortfall was disastrous on both sides of the mountain range. And in many of the rivers, the seasonality almost completely disappeared. There was no flood peak anymore. So then this complementarity doesn't help at all either. So we need some other strategy. And then we decided to look at, well, what is the seasonality in this shortfall? How does it differ from, because this is just the average across the year. How does that differ from month to month? So this graph shows the seasonal shortfall for different months of the year, January to December, for one specific river, the Paute River, which is this one here, which contains probably the most important hydropower complex in Ecuador, the Complejo Paute, where we see that the shortfall was strongest in the season July, August, September. So this was really where the river should have been carrying most water, but did not do so at all. So the period in which normally you are relying on the reservoir being filled up again. Then we looked at the potential for solar and wind power in Ecuador. Why? Because if you can somehow exploit solar and wind power in a way that helps to make the power system more resilient to droughts, the advantage is that you don't have to buy any fuel. The sun and the wind are for free. You just need to build the power plants. But after that, you'd never have to buy the fuel. So is there any way that this could work? If you look at the seasonal profiles of solar and wind, you see something very interesting. Here in Belgium, everyone knows that solar power will produce more in the summer compared to the winter. Most people know that the wind blows more in the winter than in the summer. How is it in Ecuador? Very interestingly, we see that mostly wind power and to a lesser extent also solar power reach their highest potential in precisely the same period where in this disaster year 2024 the biggest shortfall of river flow occurred. So that by itself doesn't necessarily have to mean anything. We have to investigate further, but this is an interesting starting point that maybe there is something to be done here in terms of this synergy between the resources that seems to appear in extremely dry years. So we decided to investigate that further. The question being, what would the introduction on a large scale of solar and wind power in Ecuador have changed, if anything, about this electricity crisis in 2023 and 24? And could it avoid this happening again in the future? And if so, what would we need to do? That has, I would say, two aspects. The first aspect concerns the reservoir management, so the management of hydropower lakes and avoiding that these lakes empty too much, which was one of the reasons for all these blackouts in 2024, that there was simply no water left in the reservoirs. So the reservoir management is one thing. The other one is zooming out, looking at the power system as a whole, including the thermal power plants that Ecuador has. And this is what we call power system adequacy. So looking at if there is actually sufficient capacity to always respond to demand. We have scientific models, numerical models that we use to replicate the behavior of different types of power plants in energy systems, including detailed models on how hydropower plants function based on all kinds of climate data input and hydrological data input, so river flows and evaporation and rainfall on the reservoir lakes, technical limitations of the different turbines, environmental restrictions, lake levels, and so on and so forth, that we have developed over the years. And we used these models in order to model the behavior of this Complejo Paute, the Paute hydroelectric complex on the Paute River, which I already mentioned. Why this one in particular? Because it's, aside from being the biggest concentration of hydropower capacity in one location in the country, it also contains the most storage capacity. So that means the amount of regulation, the amount of water you can store in one season and use it in another season, is highest there. This is necessary if you want to use solar and wind power, because the sun does not always shine, the wind does not always blow. We know this in advance. So you need some amount of storage capacity just to be able to cover those periods where, like during nighttime when there is no sunlight, for example. So let's focus on this hydroelectric complex. Our model is able to replicate with satisfying accuracy several of the key operational parameters of this hydropower complex, which consists of 3 hydropower plants downstream of each other, including 2 big storage lakes. So we can reproduce the fluctuations in water levels in the lakes, as well as the yearly power generation, including the shortfall in power generation during the crisis year. And most interestingly, we can even reproduce the amount of, again, with not perfect, but satisfying accuracy, the amount of shutdowns, the amount of times that this hydropower complex had to be shut down during the crisis year 2024. The orange line is from our model. The black line is what actually happened, so the official data from the power system operator in Ecuador, where we see that there was a period in the beginning of 2024 where the shutdowns already reached some relatively high levels. Then they dropped down again during the very short rainy season of that year. And then the worst period of the year started with almost half the month of November. This hydropower plant was not active. There was not enough water. So this is quite satisfying. Our model is able to reproduce this with good accuracy. So now we can explore some alternative scenarios. So what we did was design 4 scenarios. The first one is what I just showed you. So the reference, where we only consider hydropower, no combination with solar or wind at all. So this is the current situation. In scenario 2, we add solar PV. So we assume that there's some solar photovoltaic plants installed in the vicinity, and then we adapt the operation of the hydropower plant basically to become a joint operation with the solar. So the 2 should work together to respond to the demand, which means that when you have a lot of sunlight, you can keep some more water in the reservoir. When the sun does not shine, we release the water again. Scenario 3, we do the same thing, but we also add wind power, which has different characteristics. It doesn't have the same day-night cycle as solar power. And then in scenario 4, it's basically scenario 3, but on drugs. Just adding a lot more solar and wind. And we see something quite interesting that happens. This graph I will explain. What we show here is the over the course of a year, so from January to December, the percentage of filling of the reservoirs in this hydropower complex. So the amount to which the lakes are full. This range here on the top is what we have observed historically in the period 2011 till 2022, which were more or less climatically normal years. They're not very extreme. So as I said, you always have a period where the reservoir is refilling and being filled up to the max around July, August, September. and then it follows this cycle from year to year. This blue line is 2023, the red line is 2024. So in 2023, you can see that because of this El Nino, because the rainy season failed, the reservoirs could not be filled up to the necessary level until they started then dropping down again. So when 2024 started, they already didn't have a lot of water left. And then 2024 was even drier. Yeah. So during large parts of the year, the reservoirs were basically operating very close to their minimal level, which explains all these moments that the plants had to be shut down, and as a consequence, the blackouts across the country. This is scenario 1. If we look at the other scenarios, from 2 to 3 to 4, we see that something interesting changes, which is that there seems to be a sort of lifting up of these lake levels in the critical periods. And if we count the amount of shutdowns, the total length of shutdowns of these hydropower complex in 2024, which was 57 days in reality, and also according to our model, this would have reduced to 51 under scenario 2, then 42, and then 30 days under scenario 4. So apparently solar, the combination with solar and wind helps to improve the operation of the hydropower plant during a drought. 30 days is still a lot, of course, but it's half of what you had in reality, so it's a lot better. Why? Because of this synergy that I mentioned, that we see in extreme years. Because solar and wind power are most strongly present in this part of the year when the reservoirs are supposed to refill. So if you have a very dry year in which the flood peak of the river has disappeared to a large extent, this is beneficial because you can use the solar and wind power in this season instead of hydropower. So the little water that the river is still carrying can be stored in the reservoir to lift up the water levels, and then you can use it later in the year to prevent blackouts in October, November. So it alleviates the problems during the worst part or during the failed rainy season, so that you have more water stored for the most difficult part of the year. 30 days, as I said, is still a lot. How can we reduce it to 0? Now, there's another thing we can think of, given this idea of adding solar and wind power. We can also just say, why don't we operate this hydropower reservoir generally in a more careful, more prudent way? Which means even during normal years, we will on purpose keep more water in the reservoir. There's a price to pay. We will produce less electricity in normal years, it's true. But we will make sure that the water levels are structurally higher, so that when a dry year comes, we are in a better situation to ride through the crisis. So here you see the difference that would make. The same graph again, with the percentage filling level of the storage lakes. This is for, let's say, regular operation, and on the right-hand side for an alternative where we are more prudent, even in normal years, with the hydropower management. And this is, you can see this is much, much better. In 2023, we could have basically more or less followed a normal refill cycle. And in 2024, the situation would only have become critical at the very, very end of the year. But much, much better. There is a price to pay, because it means that we would have to accept a drop of about 3% less hydropower generation in normal years. Doesn't sound like a lot, but it can be a lot. On the positive side, in 2024, the crisis year, we would have produced 9% more electricity. And this 3%, of course, is nothing compared to the amount of solar and wind that we can add in the other scenarios. So if we look at these other scenario 2, 3, and 4, where we add solar and wind easily compensate for this 3%. It's actually, they can even go much beyond that, plus 10, plus 20%. So we can now think about combining the two. We build more solar and wind power, and we operate the hydropower in a generally more prudent way. What would this have meant for the crisis? And I will show this graphically. in a different way, comparing the two scenarios on both extremes. Scenario 1, no solar and wind power under normal operation, and scenario 4 with solar and wind power and with more prudent hydropower operation. Okay, so basically no measures at all compared to all measures together. What do we see here? This is a graph showing the power generation mix in Ecuador for the year 2024, January to December, and how it's made up of hydropower and needs for thermal power, to some extent imports. So this is on a seasonal basis, and then I've just taken 3 random days of the year, and show here on the right side how at an hourly level, so for each hour of the day, the power generation would have looked like. So what do we see? There was a part of the year in 2024, as we've seen, with no shutdowns of the hydropower plant. This was around May, June, where Ecuador was even able to export some quantities of power to its neighbors. This is in line with what the grid operator reported. But then the problems started happening in August, September, when some periodic shutdowns of hydropower plants in the complex had to be introduced. And it became really disastrous around October, November, when the hydropower complex was basically constantly shutting down, turning off and on again, because lake levels were always around the minimum. And this is why the government had to introduce those blackouts of up to 12 hours a day, because you can see here that during the moments of peak electricity demand, if that coincides with a shutdown of the hydropower plant, you have a huge amount of capacity that needs to be filled by the thermal plants. Well, first of all, there were simply not enough thermal plants in the country. And secondly, there was not enough fuel to power them. And this is what caused the lack of capacity adequacy. This situation is much better in this scenario, with all this solar and wind added and with more prudent operation. It enhances the potential for export during part of the year. Ecuador could export more power to its neighbors, but more importantly, it avoids shutdowns of the hydro complex during many months of the year, according to the mechanism I showed earlier. And even in the worst parts of the year, there would still have been some problems, but very mitigated shutdowns, very light shutdowns of the hydropower plant. And the amount of capacity needed to respond to peak demands would have been much, much smaller compared to the other situation. So less need for additional fuel imports, less need for building new thermal capacity. And this is not because solar and wind power are guaranteed to be available in that moment, because you never know. Sometimes the wind stops blowing, but it's because solar and wind power are guaranteed to be available, especially in this critical period, July, August, September, which helps the reservoirs to refill more easily, even in a very dry year. And this is guaranteed despite the fact that you never know exactly at which hour the wind is going to blow. But on a seasonal level, you know, these profiles are robust, just like in Europe, the sun shines more strongly in July than in January. So we find that if we build large scale, really gigawatt scale solar and wind power plants in suitable locations in Ecuador, the impact of an electricity crisis like 2024 could be to a large extent mitigated without this need to import, like to procure emergency imports of fossil fuels. It requires some changes. It requires that the reservoir operation, the hydropower operation, adapts to the production of solar and wind power. So this needs some, change in day-to-day work of the plant operators, but this is possible. And under those conditions, it would have been possible to largely avoid shutdowns of the most important hydropower complex in Ecuador in 2024, despite the drought, which was the most extreme drought in around 40 years in the region. Doing that, giving some numbers now, this would have reduced the capacity deficit that Ecuador suffered by 50% and almost eliminated the generation. deficit by minus 90%. That is still some deficit left over, but this can easily be covered, according to our calculations, by additional interconnectors with neighboring countries, like to Peru and Colombia, for example, which are already being built. So there are good opportunities for further, let's say, combination of this strategy with increased connection to the neighboring countries. Ecuador can export more solar and wind power during part of the year to Colombia and Peru, and those countries can support Ecuador in case of drought, because the needs for that would be to a big extent already met by solar and wind in Ecuador. Voila, maybe just to thank our collaborators. This is a joint venture, I can say, between Belgium and Ecuador in collaboration with our colleagues at Jachai Tech University, currently under review in Scientific Journal. And I will stop there. Thank you.
Thank you. And so we're now going to have a little debate and questions about the lectures, but maybe I'm going to let the speakers themselves talk if they want to ask some questions to the other people. And then I let the audience talk. I have some questions to all of you, but I don't know. Wait, it's difficult with the 3 lectures to switch back mentally to the first one. One of your last pictures, you said there, I saw there was something like a street or so, and you said that it depended, there's a difference in the situation of the soil from one meter to the other. How does that come? Is there water under it? Is it a matter of the water?
Yeah, so you are talking about those water tracks.
Yeah.
So there is actually a history of the summer, exactly like it was shown here for if there is a drought. Here, if we have a very dry summer, we start freezing the system with a very dry active layer. So with less water, it keeps the soil colder. If we have a very wet summer, we have a very wet active layer, and the water helps also the heat to transfer in the ground. And so it means this is when it gets wetter, it also gets deeper. The thawing is more effective. And the next year, it means the active layer is deeper.
And because of activity, it heats up. And
yeah, again, so that's actually when the system starts to thaw deeper, it's actually melting the ice, creating subsidence, because the ice is lost, so there is void that is created in the pores of the ground, so that there is subsidence, collapse. And that collapse is creating accumulation of snow in the winter. And because snow is insulating the system, it's also warming the ground. And that means that it contributes to thaw deeper again and to create more collapse and more subsidence. So once the cycle is initiated, those water tracks, they are actually location where it gets deeper and deeper every year, because it's already a location where it's warmer, the permafrost is deeper, and there is more water circulating. So everything is combined to lead to a deeper permafrost day.
Mm-hmm. And you say that in the models that we have now, that the effect of the permafrost is not incalculated, so which means everything that escapes as methane and CO2. Do you mean that nothing is incalculated, or the extra that you found out? And how do we have to imagine this extra? What is going to be the effect on the model?
So there is actually No, it's known that there is this reservoir. At least it has been quantified in the last report from the IPCC. But what is not quantified is the emission. So it's known as a fixed pool reservoir in the ground, and it's recognized that these emissions are contributing to amplify the warming of the Arctic. But what is not considered, because it's not quantified precisely, is how much in total of this pool is going to be emitted. How fast, because it's non-linear, it's clearly going to occur as sometimes it's accelerating because we have a warmer year, sometimes it's flattening. So how fast? And then the last unknown is what is the proportion between CO2 and methane? And we know that the methane has a global warming potential that is way much higher than the CO2 at the level of the century. So that unknown is critical. And right now we know it depends on how wet the Arctic will become. When it's wetter, there is more methane that is being emitted. And it's clearly the biggest uncertainty at the moment to be able to project these scenarios is how much the hydrology is going to change. If we don't know that, if we cannot model that properly, then there is very high uncertainty on how CO2 and methane will evolve. So that's the reason right at the moment, there is a number of scenarios depending on how warm it's going to be, etc. But there is no specific values that is being included in the model because of the uncertainty.
So you cannot generate any simulations.
So there are a numbers of simulations, but which one is the right one?
Exactly.
Yeah, they are. Yeah, there are numbers. But the problem is those simulations, they are made by the scientific community, but they are not included in the calculation of the carbon budget that is left to meet the 1.5 or 2 degrees maximum. Because at the moment, the permafrost emissions, it's like if you have an additional country that is also emitting greenhouse gases, but that is not included in the total calculation of the global carbon budget left to meet 1.5 or 2 degrees.
Why is not included?
It's because that number is not precise, and so. But either you can decide to include it as the maximum value, and which would be the more sensitive way to do it. But then it means that you reduce also the capacity for the country. So that's always the question. Yes, of course, the most sensitive things to do would be, okay, let's take the worst case scenario and let's stick to that. Yeah, but if we do that right now, we have like zero emission. We have to be zero. No, not 2050, not 2030. Like no.
It makes sense.
Yeah, it would. But I mean, that's the reason why it's not included yet.
So when it warms, when it thaws, then the bacteria, they produce heat. So that we get more methane and CO2. So the atmosphere heats up more, and so we get a vicious circle. When there is 2 times more carbon in the permafrost than than what is now in the air, people imagined such a runaway scenario where exponentially we get cooked.
Okay, but so there is sometimes this idea that this is like a bomb, a carbon bomb. Mm-hmm. This is also very exotic way to think of the system, because it's not like in one go. It's progressive because the thawing is gradual all across the Arctic, and in some location it's brutal and more abrupt. But in any case, you never release a large amount of carbon in one way. So it's a progressive release. What is clear is that it is currently releasing more carbon, but is it between 5 or 15% of that carbon that will be emitted? That is still unknown. It's clear that there is more carbon that is being emitted from the thaw, but it's not like a carbon bomb. Clearly, this scenario is also mediatically propagated, but it's not real. It's considered though as a tipping point. Sometimes it's called like this, because there is no way back. So everything that is thawing now, it's not going to be freezing back again. And even if we do stop completely the emissions now, there is some continuous warming effect that will continue to thaw the permafrost in the future. So we cannot stop immediately the thawing of the permafrost.
And also Putin and these days also Trump are more interested that it's not that it gets thawed as quick as possible. Start their activities over there.
That's another issue.
That's another issue. Yeah. Well, it's the same issue, but another side of the problem.
Yeah.
About your work, you studied architecture, right?
Mm-hmm.
So for me, as a sound artist, I feel that a lot of your work is very spatial, and that so also there was one work where you even showed the light effects and not the sound effects of it.
Mm-hmm.
And so I feel a lot of that you think in terms of experience in the space, not only sound, but also in experiencing the space. Also, well, I'm curious about this foils that you used as amplifiers, because they look very nice, but also spatial, very architectural, and how they work. It looks fascinating.
Well, it's based on a sheet that is that has a crystalline structure, and because of this, when you screen print layers of inductive materials, not conductive materials, on both sides, you can activate this foil, so it starts to vibrate. And so what we did with the University of Hasselt, we find a way to screen print also phosphorus pigments onto it. So that means that you can add light to it. So it's electro phosphorus materials that are also reacting on the electricity that is input for the sound. So it uses the same energy as the sound gives.
Mm-hmm.
So it reacts both ways in sound, but also in light. So if there's a lot of peaks, the light will give more. There will be more light and so on. So these sheets can have different dimension. You can screen print it, so it's quite easy to do. But it's very nice material. Yeah.
And sound quality of it?
The sound quality is you have to imagine that it's not like a normal speaker. It's more like high frequency speaker.
High frequency.
Yeah.
I cannot do it, but I can imagine thunder is also with something.
Yes. It could work, but then you have to stretch it. So you have to find other ways to have control over the way it moves.
Yeah.
It was a collaboration with Hasselt, where we just found out that there was sound into these sheets, and then by adding these electroluminescent paints, we could also use the same energy. So it's very interesting. And then of course you can also work with different colors. So we use different pigments on top of these luminescent the electroluminescent pigments. So then you have different colors.
Nice.
I found that the sounds of this melting and freezing sounded a lot like the sound effects in this movie Ice Age. No? Or even like this Hollywood things like The Day After Tomorrow, this movie, the movie.
Yeah.
Like, I don't know how they do it, but
probably
has some, I think it has some applications in movie industry.
Yeah, you're certainly right. But actually, you can really play with it if you use, for example, water with gas in it. Then you have some bubbles. But if you freeze it, and and you amplify this gives a totally different sound.
Like volcanic eruption, or
More like very tiny pops, but much more concentrated, and then it becomes like very
Have you generated a database of all the sounds that you create through that?
no. No, that's another work.
But just like out of curiosity, because create some.
So, what do you?
To make a database, you mean, and then
I have seen once filmed in Alcor Cryonics. So it's in Arizona, where they freeze in people, but then they also freeze in the heads. So when I was there, somebody died and they froze in their head with the idea that or they can gather the information to restore this person's mind on the computer, or that they would grow a new body under it or so, whatever. The problem is the cracks. So they add antifreeze. They change the blood slowly into antifreeze while they do the freezing. But they record every crack. So they collect the corpse or the head together with the whole data list of all the cracks that happened, and they tried also to localize where the cracks were also. So who knows that one day someone will be able to analyze all those data to be able where the and so on.
Have you tried recording these sounds in natural environment for the freezing or melting? And,
yes, I did
Yeah.
that, of course, yeah.
and are they different?
It's much slower. That process is, of course,
course,
much slower. So it's much more like, it takes time to, and then it's like when you put a microphone into water and there's just a lake. Then it's very you have to take your time to listen to it. So it's this is like very active. What I do. And what in lakes and so on, it's very slow, it takes time. So you need also other devices to record that kind of sound.
Maybe it would be nice to take a real permafrost sounds of.
It's also very unpredictable what will be happening there. So, with special devices that can regulate the volumes of sound that are happening.
I have a question for you, Sebastian. So the dry season in Ecuador is in August. So Ecuador is around the equator, but so it's not a matter of summer and winter. But I was thinking, in how far do glaciers still play a role there? I know that that's the area where the glaciers are melting the fastest, I think, and are a lot of gone already. So because I was thinking that the melting of the glaciers and snow give a continuation, but that's not the point, and that's not the case anymore.
I mean, the dry season indeed on both sides of the mountains is roughly around October, November, December, January. This is the driest part of the year. And then on both sides, the wet season kind of depends where. It's a bit different on the Pacific and the Amazonian side.
But I thought that they have the most problems in July.
Because this was the failed rainy season, not the dry season. That's not the same thing.
Okay.
Yes.
Yeah. Okay.
Yes. A dry season is supposed to be dry.
Yeah.
It's okay.
Yeah.
Yes. But okay. Yes. So in terms of glaciers, there are some glaciers in Ecuador. There has been a big loss. I think probably about 50% or so has been lost so far. I don't know what the numbers are more generally for Latin America. But in this story around energy generation, it doesn't necessarily have the same importance as in a country like, I don't know, like Switzerland, for example. In like a lot of the big rivers in Europe, a lot of the river flow peak especially is driven by snow melt in river like the Rhine, for example. So in countries like Norway or Switzerland that have a lot of hydropower in the high mountains, this can make a difference, which will actually first of all lead to more hydropower potential because you have more water, and then once the glaciers are fully gone, then it drops. This is not that important in Ecuador. The water budget in the rivers is not determined to a very big extent by, I mean, there is some contribution, but it's more rainfall driven. Yeah. So in climate change context, it's more important to look at what happens to the rainfall in the future, not what happens with the glaciers for river flow and hydropower purposes. Yeah. But it's true that their climate change studies indicate that there may be more extreme droughts in the future, maybe more variability from year to year in the future, not just affecting Ecuador, but the whole region. This drought in 23-24 was also not isolated to Ecuador only. Brazil was also affected. It's also a very hydropower dependent country. So this is quite important for the future. Yeah.
In Europe?
I mean, Europe is not as dependent on hydropower. Yeah. If you look at Europe as a whole, but individual countries are, and Norway has also. Norway, for example, they haven't had blackouts like this, but they have had. They export quite a lot of electricity to neighboring countries, and they've had to reduce that drastically in recent years because of droughts in different years. With I think the government had to put limits on exportations of electricity so that there would be enough for Norway. So it's something you see happening everywhere. Also in China has had problems like this, different countries in Africa also, Zimbabwe, Zambia.
But as you say, I would just think that because of the melting of the glaciers, we have a non-stop too much water at this moment until the glaciers start to vanish.
Yeah, in regions where river flow is primarily driven by glacier melt, like seasonal glacier melt in during warm season, this could happen. That in regions like, I don't know, Tibet, for example, the Himalaya, or parts of Norway, this could happen. That on the near term, Iceland maybe, that with more of this glacier melt, you see a short-term increase in potential. Although normally you would have to build more hydropower plants to really exploit it, because these reservoirs are like the size is dimensioned on historical availability of water. So if you suddenly have much more water from that same river, it just means the reservoir will overflow. You don't have the space to store it. So there's not necessarily, or even the turbines may not be able to turbine all of it. So because your power capacity is also dimensioned on the historical size of the river. So having more water suddenly having more water doesn't mean automatically you can produce much more power structurally. And it's the same actually when you talk about increasing variability between wet and dry years because of climate change. Then I sometimes get the question, well, but don't if dry years become drier, it's a problem, but the wet years also get wetter, so doesn't that compensate? But for the same reason, it doesn't, because usually you cannot store this excess water.
But unless you make more basins.
Unless you build more reservoirs.
So that would be the answer for melting glaciers, that you make artificial more basins where you can collect it.
Yes, but that would only help temporarily, because at some point the glaciers are gone. And then there is...
Yeah, but there is rain. They were collected, so...
Yeah,
but it's a collection of thousands of years.
It's not the same amount of,
And on a related question, you said in your presentation that the seasonality gets flattened because the peak is less high, because you during the drought...
The peak of what?
The difference in the seasonality, you said that it gets more flat.
But the seasonality in what? In which parameter?
In the discharge, the river discharge.
Yeah.
And so
is
it expected in the future to be more and more the case that you have less difference between peak flow and low discharge? Or is it going to be a problem that the seasonality is...
Okay, I get the question. I think the short answer is yes. If you say the difference between peak flow and low flow is reduced, this is a very scientific way of saying it.
Yeah.
What happens in reality is simply that the wet season fails.
Okay. And this
so the rains are supposed to come in a certain part of the year, like like the monsoon in India, and they just don't. They fail. They just fail to show up, so to speak.
Globally, there is reduction in the global precipitation, or it's more like it's less even distributed.
No, we cannot say there's a global reduction in this, but we can also not say there is a global reduction even in the case of Ecuador in the Amazon basin, but we can say that there is a trend that the extremes become more extreme.
Okay.
So that the effect of El Nino on drought and river discharge becomes more pronounced in the future. Okay. And at the same time, it may be that wet years, that years in which have more rainfall than normally, with a wetter rainy season than normally, become even wetter.
Okay.
But this doesn't help to compensate for the dry years because you don't have the storage to store that water.
Exactly.
So it's a
Okay.
Unless the mountains are filled with
but
baskets.
This is this is a sensitive discussion also for ecological reasons. Building a reservoir can have quite big environmental impacts. So it's not that easy to build new hydropower reservoirs because there's not so much money necessarily. There is investors are not necessarily. Back in the 60s or 70s, there was this kind of hydropower boom, where the World Bank was just investing in crazy hydropower projects everywhere, flooding massive areas. But this is because now we know that this has really negative effects for biodiversity and
also the carbon footprint, right?
Yeah, and carbon because of methane emissions from reservoirs in some regions. These reservoirs in Ecuador are quite good examples of hydropower reservoirs with relatively low impact because they are built in valleys that are extremely narrow, so like high and narrow. So with a relatively small or like a relatively narrow dam, you can fill up the valley. Usually nobody lived there because on that steep terrain, no one can live. There's no agriculture land that is lost. And the surface, the lake, it will be a quite deep lake, but with a little surface area. So this reduces the amount of methane emissions. There's still biodiversity loss. There are still impacts, but those are let's say still the best practice examples you can find. And you also have to have the space for building additional reservoirs. Sometimes that space is already taken by existing. It's not that easy. You can just build more.
But you had one drawing where you saw the different basins.
But this only makes sense in the locations where the drop and also where the drop is the steepest. You need at least a couple of 100 meters in this case for the water to drop.
Where also it is like you say, like it's
so
narrow enough when it's a whole valley, then you can.
And if the first reservoir is at the, let's say at the top of the slope, like where the mountains convert into lowland, and the last one is at the bottom, then where else are you going to build? It's already it's already taken. It makes no sense. So this is
it's just a theoretical question.
Question for Sophie, with all your permafrost knowledge in disaster watching, are you connected with activists or organizations that go and discuss with the ruling people? Or not at all?
So the work that my position as a scientist is to quantify what we see and to produce the research that is then can be used into this report that is communicated. So we do communicate the work that we do to politic actor is to actually contribute to the report. For example, we are revising right now the EU position relative to the strategy in the Arctic, because the text that was last published is 2021, and the geopolitical situation has much evolved since then in the Arctic, and so the EU has to revise the text that was the guidelines for 2021. And so the community is asked to revise depending on their expertise. And permafrost is definitely in the middle of the text because it has impact on infrastructure, on mobility of people, also on the access to several resources that are in the center of the geopolitical questions. And so in that way, I consider that I contribute to provide input. This is, to me, a different way to contribute than being myself activist. I don't consider myself as an activist. I have a different role to play as a scientist, but I do consider that this is where we can be active, giving input on text for the EU to have that such a text. I think it's key that the EU is positioning in the Arctic and to preserve the land there and to prevent from any misuse of the land.
So they do read
Yeah,
texts.
there is a very big concern about
because you immediately you are also giving your opinions on the EU people. You said in the introduction, you are an advisor.
No, I also work for the EU, but I'm not allowed to talk about that.
Okay.
A question for you: is there ever also a discussion on using less energy, using less electricity, so that we don't have to? Because that is going up and keeps going up.
The discussion exists, and I think in countries that you would call part of the developed world, this is maybe a reasonable discussion. But my opinion is that in countries where demand is still rising that much, like what we see in Ecuador, this means that there is a lot of demand that is not being met. Certain living standards are being aspired that are not met by big parts of the population. I don't think that the debate should be about reducing energy use in countries that have not, achieved the level of industrialization or welfare of a country like Belgium. Of course, we can talk about energy efficiency, just having more efficient appliances, more efficient laptops and microphones, and this is, I think, generally an important topic. But reducing energy use, I don't see it as a goal in itself, but that's my opinion.
I also think that reducing electricity, so first of all, when we replace carbon or fossil energy, we will replace it by electricity. And also when you see with the AI, and so that we will have a gigantic growth of electricity, and that's what we have to foresee. So when they're now building data centers that are as big as Manhattan, consuming electricity like a whole country, then
I think that's where how can we reduce it rather than, because it keeps on growing and we know that we can't keep up. I mean, it's obvious.
I mean, but
have that issue.
You can have growing electricity use, but still reducing overall energy demand. If we start all driving electric vehicles.
Or stop driving vehicles?
No. Yeah. If we all stop driving, if we replace the existing fleet with electric vehicles, then we'll have a lot more electricity demand. But since electric vehicles are energetically more efficient than gasoline cars, overall energy use will go down. just a bigger part of it will be electricity. Yeah.
Okay, are there more questions? No. I have one small silly question for you, Sophie. Sorry, but your last picture fascinated me in the sense that you saw this delta of rivers that were frozen. I think so. The water was higher than the soil. So
It's because it's filled in snow.
it's filled in snow.
Snow, yes.
I was thinking that because of the ice expands, that the rivers come more up. So no, that's not the
It was
case.
filled in snow. You can get really deep in snow, I can tell, in these
Yeah,
water tracks.
but you see the rivers, but the rivers are
It's
that
maybe
much higher.
the photo looked like it, but it's really.
It's not, no, it looked like that, like the shadow that it really was.
Maybe
Was,
it's,
instead of deeper, it was higher. Okay, well, I think then we're done. I thank you all for coming and to participate in the debate.
Thank you for coming to participate. Thank you very much for people who were following us. So just it's no question, but it's okay.
Okay.
And yeah, so just it will be after edited and put on the website, just on YouTube. So just if you would like to see it again and just to listen, so just you're welcome. And thank you very much for Nadine to have us like a guest here.
Okay, thank you.
Thank you.